All right. I guess most of you don't know me. My name is Fernanda. I'm a postdoc at University of Queensland, and my supervisor is Stefan Bowman, and he is uh, the leader behind Neurodesk. So I've learned a lot from him, but I'm not as good as he is with software development. Um, so, so today I will essentially show you how you can use a deep learning model to predict retinotopic maps from brain structure. So you wouldn't need to acquire empirical data and hopefully save some time and money. And I will also show the potential of using these predicted maps for automatic visual area parcellation. So again, you would skip all the previous step of annotating retinotopic maps yourselves and generating the parcels. So the tool that I'm gonna show is DeepRetinotopy. Is a tool that I've been developing for the past year. And this tool is composed of three main components: the pre-processing pipeline that uses FreeSurfer and Connectome Workbench, DeepRetinotopy, which is the deep learning model I developed in my PhD, and also the visual, not a visual area delineation, but a first step. And here we essentially generate visual field sign maps. And all these components are already packaged into software containers. They are available as Docker containers and Singularity containers on your desk. So hopefully it will be useful for some of you. So in the first part of this session, I will demonstrate how you can use this tool and DeepRetinotopy to generate retinotopic maps. Well, I think now you all are aware that our visual cortex is retinotopically organized. That means that adjacent points in the visual field here are mapped by adjacent points in the visual cortex. And we usually represent the visual field in terms of polar coordinates, so polar angle and radius, but we call radius eccentricity. And on here we have a representation of polar angles in early visual areas, and this is just an unfolded representation of polar angle map. And one key characteristic of these maps is that you see multiple polar angle reversals, just like Noah said previously. And just to clarify this, we can look at the dorsal portion of early visual areas, for example. Along the calcarine sulcus, we have the representation of the angle 360 degrees, like here. And as we move across dorsal V1 all the way to dorsal V2, we see that these angles decrease in value to 270 degrees. And cool. And then when we move across dorsal V2 to dorsal V3, we see that these angles now start to increase to 360 degrees. And once we are in dorsal V3 and move across dorsal V3 to the border of dorsal V3 with higher order visual areas, we see that these angles decrease once again. So we see multiple reversals of polar angle representation, and where we see these reversals is essentially where we draw the boundaries that you can see here in white, and this is pretty much what you guys done in the previous session. So a clear utility to acquire this empirical retinotopic mapping data is to delineate boundaries between visual areas, right? But the acquisition of experimental data is time consuming. It can take from 15 to 60 minutes to acquire retinotopic mapping data. It is expensive. I think some of you are very lucky that can acquire for free. In Australia, a 1-hour session at the 70 is about $1,000. So it's quite expensive, and it's often not viable for some clinical populations. So, there was a really great effort in the literature from researchers trying to propose an alternative method to that. And these alternative methods are essentially models. And these models take advantage of this key idea that the representation of the visual field has a fixed location in the visual cortex. So we can model that, right? And it's funny because the three of us are, you know, a couple of, we are amongst these researchers that have contributed with models of retinotopy. And today I will show the model that I've built in my PhD, DeepRetinotopy. And DeepRetinotopy is the main component of this toolbox that I've been developing. DeepRetinotopy is a geometric deep learning model. So it's just a fancy type of geometric deep learning models that allow us to learn representations on cortical surface models. And you will see that it really makes sense to use geometric deep learning in the next slide. But we built this model to essentially learn this complex relationship between the function organization of the visual cortex, retinotopic organization, and the underlying structure. And that is because even though retinotopic maps are very similar across people, there is still some variability, and this variability has been linked with underlying variability in underlying structure of the visual cortex, for example, cortical folding patterns. So to build this model, we use as the input the surface topology, essentially how the vertices defining this surface are connected with one another. We use the vertices coordinates, so essentially the location of the vertices in the 3D space. And we also use feature vectors, which are essentially the features associated with each vertex. In this paper published in 2021, we use curvature and myelin values. So they were our features. As the output of our model, we expected polar angle and eccentricity values for every single vertex. So this is essentially a vertex-wise regression task. Why geometric deep learning? Well, that is because in neuroscience, we often represent brain structure and function on cortical surface models of the brain. And we do that because many of those features only make sense when we consider the intricate cortical folding of the brain, right? And these surfaces are essentially discrete graphs that are folded up in the 3D space to resemble the actual shape of the brain. And the nodes of this graph are connected to form triangular faces, like you can see here. And this kind of data representation is also known as non-Euclidean data. And one important feature of this non-Euclidean nature of this data representation is, for example, the distance between 2 points on opposite banks of a sulcus. If we were to consider the Euclidean distance, we would think that, we would find out that these 2 points are close to one another. And in the context of retinotopic mapping, we would think, oh, these 2 points are mapping positions that are close to each other in the visual field. But that is not the case. We have to actually consider the cortical distance, the distance along the surface. And if we do so, we find out that these 2 points are actually mapping positions that are really far apart in the visual field. So it really makes sense to represent retinotopic maps on surfaces, and therefore we went for a geometric deep learning kind of approach. To train these models, we use the Human Connectome Project dataset, which includes high resolution data from 181 participants, and they made available anatomical data in the form of curvature and myelin maps, and the functional data in the form of polar angle and eccentricity maps. And here is the performance of our model. So on the top row, we have the ground truth retinotopic maps for both left and right hemisphere, as you can see here, for one participant in our test set. And nice, I think you guys are already used to seeing a retinotopic maps at this point. And in the bottom row, we have the predictions. So it's pretty cool to see that our model was actually able to capture these polar angle reversals. It predicts really well also eccentricity maps, so very happy about it. But I think what we were particularly happy about was to see that our model was also able to predict individual variability in retinotopic maps. So like Noah was saying before, the subject he was showing had this very strange Y-shaped representation of the lower vertical meridian, the yellow, would be the yellow color on here. And we actually see one individual that has that Y-shaped representation. And yeah, these are all left hemispheres. But we also notice that, for example, participant 2, 3, and 4 show this discontinuous representation of the lower vertical meridian, and that those yellow band would represent the border of dorsal V3 with higher order visual areas. So, you know, a lot of variability here. And the cool stuff is that DeepRetinotopy can predict that. So our model was able to predict these discontinuities for participant 2, 3, and 4, and this Y-shaped representation as well. So pretty cool. Yes? I'm sorry, I didn't get it. How do you implement it? So this is empirical retinotopic mapping data. It's just like what Noah did in the previous session. You run PRF analysis to get these retinotopic maps.
So is this the annotations or the actual map that you're creating?
The actual entire map, yes, yes. So DeepRetinotopy is for predicting retinotopic maps from structure only, okay? Unfortunately, we cannot parcellate the visual cortex with DeepRetinotopy.
You mean you predicted from structured data, no functional data?
No functional data, yes, yes. Yeah, so this is the main component of the toolbox. But in 2021, I used curvature and myelin maps as the input for our model. But most people don't, you know, acquire the data necessary to generate the myelin maps. So for the toolbox, I've retrained our models to taking only curvature maps, which is easily generated with free surfer data. So all you need to run our model is free surfer data. That's it. And yeah, I think now we can have a try. So we can go to our Jupyter hub. Oh my God, I cannot see my cursor. Now I can see it. So for you to access the Jupyter notebooks that I have on here, you have to go to shared, lecture number 3, VSS 2024 tutorials, and session 3, sorry, long path. And then you can open up the second notebook, session 3, and there we go. On here, you will find some documentation. It's not as comprehensive as Noah's documentation. I can do better, but the requirements to run DeepRetinotopy on your desk is essentially having your free surfer directory, so your preprocessed data, and you also have to download the HTTP template surfaces, but we already have it here in our shared space, so you don't need to do it. Yeah, a bit of instruction to download the surfaces whenever you want to run this notebook from scratch. And then on here, we have to start with, are you all in this notebook? Yes?
Sorry, how do you decide which HTTP template you use? I saw there's a few different ones.
Yeah, it's just the 32K one. This is...
Does anybody use the other templates for anything? I'm not the only one. For what?
Yeah.
For comparing subjects.
I've trained DeepRetinotopy with this 32K one, so this is the single one that you guys have to go for. All right. So we start by, module loading our DeepRetinotopy tool. This is the version that we are using. It's an older version. I'm, continuously improving this toolbox. I'm not a computer scientist, so I'm learning as I go. So it's not very clean, but it works. If you run which Python, you will find that the Python kernel that we would be using is the one that is available on our container. And to run DeepRetinotopy, we essentially have to run 3 lines of code at this stage. And in the next month, only 1 line. So first, I'm just defining the date tag of this toolbox. So this is the version that we are running right now from last year. And we have to navigate through the CVMFS folder where all the Singularity containers are to access the DeepRetinotopy toolbox. But in the near future, we won't have to do it. And here is our DeepRetinotopy bash script. You will notice that this script will take as input the path to the FreeSurfer directory where all your subjects are with all the preprocessed data. It will also take as input the path to the templates, essentially the HCP surfaces, and you can put in the name of your data set. And I want to generate polar angle and eccentricity map, but currently DeepRetinotopy can also generate sigma. It doesn't look super good, but it's there. And yes, and you just run it. I wouldn't recommend to run it though, because it will take a little while. So as part of the pipeline, we generate the mid-thickness surface using FreeSurfer, and then calculate the curvature of the surface and resample that curvature maps to the HCP template space. That step, the generation of the mid-thickness surface, takes about 15 minutes. And to run DeepRetinotopy, and like in this pipeline, we actually generate 5 different retinotopic maps. We take the average of those maps, and if you want, you can generate some sort of like uncertainty metric with all the other generated maps. But this whole process takes about an hour to generate polar angle eccentricity maps for the left and right hemisphere, so it's a bit slow. But if we had GPUs, it would be way faster. So instead of running this, we will simulate our data running step. So here we just have to run on our terminal window step 3.1. And this will essentially generate the retinotopic maps using DeepRetinotopy. We can navigate to that folder to have a look at what we get out of it. So if we go to our work folder and then bits, source data, FreeSurfer, and the subject. Oh, I forgot to mention, this is the same subject that you guys processed in the previous session. So you will see the generalizability of DeepRetinotopy because the model was trained on the Human Connectome Project's dataset. So we click on it and you find out that we now have a new folder, DeepRetinotopy. And if you click on it, you will see a bunch of stuff on there. What matters at this point is to see that we have the predicted eccentricity and polar angle maps in the HCP space, but we also have the predicted maps in the native space already. So if you want, you can visualize that interpolating on your native surface. Cool, nice. So we have the output, but we want to have a look at it, right? So now we go to our visualization notebook, and this is when or where our Conda environment matters. So I don't know if you guys have run the previous steps, which is Conda activate DeepRetinotopy and then pip install. No? Okay, yes, maybe. So yes, so this is the thing that you guys have to do. I can show quickly where the commands are. So if you go to shared, lecture 3, VSS 2024, tutorial session 3, and then session 3 dash visualization. You just have to make sure you activated your content environment in a terminal window and run the pip install -r requirements. But also make sure you are in the right spot to run this, because the requirements is within this folder, okay? Okay, I'll wait a few minutes. Comments, questions? Not yet, yes. Yes, it is, it is. But if you have data you want to test it, you let me know.
Do you have any measure on how close this estimation of a PRF model is to a PRF model that is generated based on functional data?
So we did, in the initial paper published in 2021, we computed how accurate the model was, but for the HCP dataset. So it's a bit annoying, right? Like in the deep learning community, it's very rarely people see the generalizability in out of distribution data. And I made this mistake then. So then I splitted the HCP dataset into training, development, and test set. So we evaluated how accurate the predictions were on our test set that was never seen by the model, and it was pretty good. But of course, this is not the ideal. I haven't validated the toolbox yet. This is currently in development, but I'm hopeful that it will be reasonable. Yeah.
Is that 7T data?
Yes.
I ran it last week on 2T data, and I wonder how accurate it's going to be. You don't know.
I don't know. Yes. Yes. I think there's a lot of room to collaborate and see how valid the predictions are. Yeah, because I think that would be quite useful for people that don't have the functional data. So yeah, I would appreciate help.
Probably depends a lot on the quality of the T1, I think.
Yeah, yeah.
So T1 quality is probably one critical parameter. So because the HCP there is, it's actually 3T T1, but it's 0.75 millimeter, and they're not too shabby. I mean, there's better T1 data out, but they're at least at 0.7 millimeters, so their surface reconstructions are reasonably good, better than what you get from a 1 millimeter T1. Yeah.
How are we? Are we good? Yes? Okay, cool. So actually, to visualize our predicted maps, we have to activate our content environment. And it's pretty cool in this like Jupyter Hub environment that you can actually switch kernels or content environments just clicking on here in the 3 dots, and then you will see that there will be all the content environments that you have available will be listed on there. And here we actually are using the DeepRetinotopy content environment. You just select that and done. Did you guys find it? Okay. Yeah, so we start this by importing the libraries that we will need for visualization. Hopefully it won't be too slow. Or maybe it will. Oh yes, we have a Discord channel. So if you guys have questions or comments for later on, you can post on there. It's called computational neuroimaging, something. Okay, cool. We imported our libraries, and now it's just like a little function so we can interact with the predictions. So this is the ID of our subject. And here I'm just defining the drop-down menus so you can interact with the different predictions and the empirical map. And on here, it's not binarized, it's more like turn the maps into a discrete form, so it's easy for us to see where the boundaries would be. And yeah, that's it. And then we can run this, and then we will be able to visualize the maps. And all this visualization is done through NiLearn. So if you want to know more about this kind of visualization, you can check out their website. But here it is. So this is the predicted average map. As I said, with the toolbox, we generate 5 different predictions from 5 different models. And this is the average predictions across all the 5 models. We can see very nicely the representation of polar angle in the ventral and dorsal portion of early visual areas. And you see that there is some sort of awkwardness here in the dorsal portion of early visual areas, right? We don't have a very clear and continuous yellow band here, which would represent the boundary between dorsal V3 and higher order visual areas. So this is cool. This is kind of expected, given what Noah have shown us in the previous session. You know, the subject had a very kind of awkward map. And if you guys click on the drop-down menu to go to the empirical data, you will see, it will take a little, oh, it didn't take too much, okay. You will see, yeah, the awkwardness is there. It's kind of here. So this color scheme is not ideal for the empirical data. It looks a bit ugly, but you get the gist. And yes, you can go through the different predictions on here. And you see that the predictions are very consistent in the sense that it always predicts this awkward yellow band in the dorsal portion of early visual areas. So this is cool. It's actually predicting individual variability even in out of distribution data, because this is NYU data set, right? But I don't know if I would say it's out of distribution, because also we are using free surfer outputs, right? I would imagine that they would be consistent, I guess. And you can also see these maps in the discrete form. And I find it very interesting to see in this discrete form, because then it's very clear how awkward this lower vertical meridian representation is in the dorsal portion of early visual cortex. So you see that we don't have a nice continuous band that is expected. And if you look at the empirical data, we have something very similar to that. Like here, you see this discontinuity here. So I find it pretty cool. And yes, I think I will give you a minute so you can, explore yourselves as well. And then we go to our last bit. Do you have questions? No? Almost done, guys. Where is my slide? Okay. Yeah, so as I said, I would appreciate people helping me with the validation of the toolbox. So if you want to contribute to this project, let me know. It's all open source. It is all available on GitHub. We already have a integration testing pipeline, so it doesn't matter what you do. We will know if you are breaking or not our pipeline here. So yes, please let me know. And here is the link for our repo. But yes, as I said, DeepRetinotopy only predicts retinotopic maps. And I think most of you would be interested in getting parcels out of it, right? And this is what people complain about, DeepRetinotopy. It's not so useful because you're just predicting retinotopic maps. And well, I've got to learn in analysis that could be a first step to automate delineation, and we could combine that with DeepRetinotopy. And this, and I will show you in a bit. So I've shown you how to generate retinotopic maps with DeepRetinotopy, and now I will show you how you can generate these visual field sign maps, which I think is the promising bit for automating delineation. So what is visual field sign maps? Essentially, in visual field sign analysis, you combine polar angle and eccentricity maps into a unique representation of the visual field, as you see here. And in this representation, adjacent visual areas have alternating signs. So for example, V1 is negative, V2 positive, and V3 negative. So it's very clear where the boundaries are. It's very objective. But most people don't use this analysis on their empirical retinotopic mapping data, because when they do it, they kind of get a crap out of it, because empirical retinotopic maps are very noisy. So the sign maps will look a bit ugly as well and not very helpful. But when we do it on, when we run this analysis on our predicted maps, we get very nice sign maps where the boundaries are kind of sharp. So I think it's quite promising for an algorithm to delineate boundaries. Yeah, so it's pretty, and that is the case because our predictions are quite smooth. But what are they? I like to think of sign maps as a representation of the sign of the rate of change. So if we have a look at this representation of a strip or line, isocentricity line on here from the dorsal portion of early visual areas, and then rotate that, we can see very clearly that up here we have the representation of the angle 360. As we move across dorsal V1 to the border with dorsal V3, we see these angles decreasing. And from there to the border with dorsal V3, these angles increase. And from there to the border with higher order visual areas, these angles decrease again, which is equivalent to something like that, a function like that. And here it is. So this is just a representation of how polar angle values vary along a isoeccentricity line, okay? And if you remember of high school lessons of how to calculate rate of change of 2 points, of given 2 points of a function, it would be something like that, right? It's angle 2 minus angle 1 divided by location 2 minus location 1. You can see here that the angle in location 2 is lower than in location 1. So if we were to calculate this rate of change, the sign of it would be negative. If we do the same for dorsal V2, we find that the sign of rate of change would be positive because angle in position 2 is higher than in position 1. And if we do the same for dorsal V3, we find that the sign is negative. So that's it. That's all what sign maps are. But usually you see in the literature that they refer to it as mirror or non-mirror image representations of the visual field, but I like to think of it as rate of change or sign of rate of change. So yes, now we go back to our notebook to generate our visual field sign maps. So where it is? Here it is. Okay, so we go back to our session 3 notebook. Scroll down, and here it is. If you haven't ran DeepRetinotopy, a couple of requirements, and it's pretty much a single line of code. It's just a Python script, and we have to pass to this Python script the path to where our predicted retinotopic maps are. So they are within the subject folder in the free surface directory. So this is all we gotta do. We can actually run it because it's quite quick. taking a little while. And you will find these sign maps back at the DeepRetinotopy folder. So if you navigate across, if you go back to your home directory and go to your work folder, beads, source data, free surfer, the subject folder, and DeepRetinotopy. Once it's done, but you will find it there regardless, you will find these two files, the field sign map for the left hemisphere and the field sign map for the right hemisphere. And these maps are, if I'm not mistaken, in the HCP standard space, but you can also generate that for the native space. You just have to check the Python script that I've put together. It's a very short one. All right, so we can go to our visualization notebook so we can check out how they look like. So if we scroll down on our visualization notebook, I've imported this function before for us to visualize the sign maps. So you just have to pass to the function takes in as arguments the subject ID, the path to the free surfer directory, and the path to the template directory, and which hemisphere you want to have a look at. We run it. There you go. We have our beautiful sign map for our generated with our predicted retinotopic maps. So you can see a very clear, sharp boundary for V1, V2, and then we see the emergence of the awkwardness in dorsal V3 here, the discontinuity. I don't know what to do with that. If you inspect the sign maps for the right hemisphere, you will find that everything looks as expected. So we have a really nice sharp boundary defining V1, defining V2, and V3. So as I said, I don't think I've mentioned, all the awkwardness that I see in retinotopic maps are usually more present in the left hemisphere. So more variability is in the left hemisphere. I don't know why, but I want to find out. Yeah, so this is it. As I said, I think this is just the first step for an algorithm that will automatically delineate the boundaries. And I think this is a good step because we can already see the boundaries between visual areas, at least for early visual areas. Questions? No? Okay. Yeah, so this is what I've prepared for you guys, but if you have questions when you run these tutorials back at home, you can email me at any time. I will try to put a bit more documentation in the notebooks as well, and we'll make it all available on our repository. And yes, I would like to take this time to acknowledge all the people that were somehow involved in this project. So Alex Bucket was my PhD supervisor, and now Stefan is my supervisor. I'm not doing much work in this area anymore, but I'm learning about software development. So, so that's why I got this toolbox kind of done. But as I said, it's a work in progress. So if you guys want to help me, you are more than welcome. Yeah, thank you. Okay.
All right, thanks everyone for coming to our workshop. We hope that you found it educational and interesting. Do expect to get an email or two from us in the next few days about the confusion over the access to the instance. We will, like we said, we will keep it up as long as we can. We have a budget that has a limit, so it kind of depends how much you guys use it. We do want you to try these things out and feel free to do so. Please don't upload your whole data set and try to analyze it on the hub instance. That would probably be all the budget we had. Please do use it. Please feel free to upload a sample subject and try it out. That's totally great. And if you have trouble with any of these tools or you want to answer questions, would like us to answer any questions about anything, feel free to email us. We're happy to help. Thanks for coming.
Zoom people, thank you.